our final For our final invited talk, it's my great pleasure to introduce Professor Zining Zhu. Professor Zining Zhu is an assistant professor at the Department of Computer Science at the Stephen Institute of Technology. He directs the Explainable and Controllable AI Lab. He is affiliated with Stevens Institute of Artificial Intelligence and the Center for Research Towards Advancing Financial Technologies. Prior to joining Stevens, he received a PhD degree at University of Toronto and Vector Institute. His research is in natural language processing and explainable AI, including understanding the mechanism and abilities of AI and incorporating the finding into controlling the AIs. Professor Zining has received paper awards at NACL. He has served as an area chair for NewWaves, ICML, and action editor for ACL Rolling Review. So let's welcome Professor Zining.
Thank you. It's been a great pleasure to share some findings of our lab's research and along these exciting directions. So it's about large language model reasoning. I have been trying to look for some ways to motivate reasoning. It seems like reasoning has been a very important topic, and it's a hot topic. Everyone is talking about that. So I thought about some ways to motivate this talk and decided that why don't we just use the headlines of the big companies' news articles. So OpenAI has been talking about reasoning in their first sentence of their news article when they are shipping the O3 model. Same as the DeepSeek, they mention reasoning both in the title of the news article and the name of the model. And Google as well, in the first sentence, they mentioned that Gemini 2.5 models is capable of reasoning through thoughts before responding, resulting in enhanced performance and improved accuracy. This is Cohere. They also named one of their models reasoning. Anthropic as well, they mentioned reasoning not in their title or the first sentence, but in the first paragraph. So it seems like reasoning has been really an area where people want to see a lot of progress in. And reasoning has been very relevant to many tasks in our daily lives. So when we plan the trips and plan the activities, we increasingly rely on the reasoning capabilities, and as well as figuring out some plans to the solutions. Many of my friends have been using coding agents or large language models to do vibe coding. And one of the steps is to figure out some plans to execute the task that is described by the programmer or the vibe coder. And in the subsequent steps, the agent needs to analyze the files, and those files may include codes, numbers, text, or even the documents with other formats and or HTML websites. After this analysis, the reasoning models are usually able to give personalized explanations of new concepts. I've been encouraging my students to use large language models when studying the concepts. And up to now, their feedback have been pretty positive. And they say that the large language models serve as sort of teaching assistants that can be really helpful. They can even help them make some flashcards or practice questions to help prepare for the exams. Of course, sometimes help do their homeworks if the homework is for the questions that allow them to use large language models. For the scientists, sometimes we are also using language models to propose some new ideas and hypotheses. Some of the ideas are actually new and doable. although there are a lot of repetitive or not doable ideas, I think there are in the future the language models are going to be better new idea proposers. So up to now we have seen a lot of promising use cases of reasoning of large language models. Let's take a look at some of the areas where reasoning could still be improved. So psychophantic behavior is one of the problems. So when humans ask the model to uh, uh, to do things, the model usually compliments the humans, saying something like, "You are absolutely right. This idea is very brilliant, and I'm absolutely going to follow that." Uh, and the psychophantic behavior could be detrimental sometimes. And yesterday, Nicholas mentioned a few very important cases where psychophantic behavior could lead to significant failures. Last year, we kind of saw this behavior as in an educational scenario. So we have been using large language models to do kind of explain some practice questions to the students. And after the students get some homework practice question feedbacks, we encourage them to ask for the large language model for explanations. And if the answers are okay, the language models could give explanations that are convincing, fluent, and this procedure can effectively help the students reinforce the knowledge. But on the other hand, sometimes when there are some typos, the explanations provided by the language models could still be very convincing and coherent, and it could lead to the students believing in that the incorrect solution was the solution to that problem, even if there are some typos. So in that case, the helpfulness is actually adversarial. Adversarial helpfulness, now I consider that as a special case of sycophantic behavior. And it could be especially detrimental when we are using language models for education purposes. Another failure is about counterfactuals. So last year we were studying the common sense reasoning behavior of the language models. We try to use the common sense reasoning trees to formulate the common sense reasoning difficulties and the procedures. So if there's a question, does hydrogen appear in the ocean? We can formulate that using this tree. So there's a node hydrogen, uh, uh, the second node water, and the first two nodes are connected by the relation part of. And the third node ocean is related to the water by a spatial relation. So with this reasoning tree, we can see that hydrogen is part of water, which is in the ocean, and therefore we can conclude that the hydrogen appears in the ocean and provide a positive affirmative answer to this question. But we can negate part of the reasoning tree. For example, if we negate the first edge part of into not part of, that effectively breaks uh, the reasoning chain. So when hydrogen is not in the water, uh, this reasoning tree does not support the case to answer positively when we are asked, does hydrogen appear in the ocean? Similarly, we can negate the other edge as well. So suppose that water does not appear in the ocean, then we cannot by relying on this tree only, then we cannot say with confidently that hydrogen appears in the ocean. So on the right-hand side shows some examples of the perturbed, or in other words, anti-factually grounded common sense reasoning trees. And each tree corresponds to a question that is conditioned on an anti-factual setting. And we realized that when we pass those texts into large language models, we explicitly tell the language model to ground on some anti-factual scenarios. The language models still rely on the existing common sense, and they will still say hydrogen is part of the ocean more than a trivial amount of time. So there are still some failures with the when we would like to introduce new information or new knowledge into the language models. So there is a subtle difference between introducing some new information to the model and asking the model to explain something incorrect. So in the adversarial helpfulness problem, the model should stick to the original common sense and provide the reasoning procedure correspondingly. But here, when we were trying to update the knowledge inside the language models, they should instead rely on the new knowledge. And there is a fine line between the case when we want the model to stick to the old knowledge or adapt to the new knowledge. And I think setting up some priorities for the language models, for example, first establishing some legislations and then adapting to the evolving world, this can be a solution. And but that might also not be the eventual solution, and the actual fine line might depend on the use case. So another failure that we have seen recently is the very lengthy thinking process of the language models. So when we work on some coding problems, uh, we give the coding agent a problem, and the agent first thinks and then makes some plans and then does the action. But sometimes they instead think and plan and then think and plan and repeat this procedure a lot of times before actually going out to act. So it thinks for unnecessarily long number of iterations. Usually after the first iteration, they already know what to do, but they just wouldn't continue to carry out these actions and call the tools. Uh, uh, this results in a lot of wasted reasoning tokens. So this problem is not limited to coding problems. We realized that for non-software engineering problems, for example, mathematical reasoning and even moral reasoning and common sense reasoning, similar behavior could sometimes occur as well. So it's also relevant to the model's confidence. And actually in column, there are two papers about, I've seen at least two papers that I mentioned overthinking. And one is called, I think, Thought Terminator. Another one is called the Missing Premises. And yeah, the overthinking is something that actually should be improved when we want to not only save some tokens when the model is reasoning, but also just improve the reasoning correctness. So today I'm going to propose some intuitions that and that leads to one of the potential solutions towards improving the reasoning. And I'm going to claim, just draw the claim there. So to understand the cause of these reasoning problems and also further provide one of the solutions to those causes, it's possible to do that through mechanistic interpretability. And by opening the black boxes of those models, we should be able to at least partially understand and control the reasoning procedures. There are two intuitions that support this claim. First one, the answer to solving those reasoning problems should be in a relatively small subnetwork of those models. And second, the actual format, the granularity of the subnetwork remains open, and there are a lot of potentials. In recent years, we have seen a lot of promising progress along the mechanistic interpretability. And this survey was from one of the workshop organizers, and they summarized the works on sparse autoencoders. So sparse autoencoders identifies the sparse dimensions from within the language models. And by selecting the proper features from those sparse features, it is possible to explain the behavior of one aspect and further to intervene on that behavior without intervening on other behavior of the language model too much. We don't need to only rely on the sparse autoencoders. There are other promising medium for steering the models. This review summarizes some recent works about, actually it summarizes quite a few, around at least 200 related works about representation-based engineering. So the language models compute a lot of intermediate representations. Some of them are meaningful, some of them do not appear that meaningful, but it is possible to figure out a lot of creative methods to steer those representations and make the models safer in many senses. For example, to make them more truthful, make them more harmless, and or even try to change some of their knowledge. Also, representation-based methods have been a field that's developing pretty fast. In the past few days in Column, I see at least 5 or 6 papers about representation-based steering. So here's a visualization of how small this subnetwork is. So it is possible to figure out a small subnetwork inside the model that has a lot of impacts to the model's behavior. So this visualization is motivated by Luke's ACL keynote talk, and we were trying to understand how large the billion is, because the large language models currently we are working with language models with number of parameters that are in the scale of billions. So imagine that one neuron corresponds to one bottle of drink, and a luggage case could correspond to the volume of around 2,000 bottle of cola, and that is around the size of a steering vector that is in a representation. And imagine that there is a basketball, and there are 10 stories of this kind of cubes, and each cube contains 10 luggage cases. And now imagine that there are 10 of such basketball courts. Then that of those 10 basketball courts, the number of bottles of cola there would be around 1 billion. So if we are going to find a vector or some even smaller subnetworks that are appearing in the language model with massive number of parameters, we are actually looking for a very small unit. And because there are so many such units, it's very likely that we are able to find a subnetwork. But on the other hand, it is likely that this subnetwork might not be the only answer, and we will need to do a lot of experiments to find the subnetwork that is a lot better than the existing ones. So here is a previous work that kind of indicates how effective can a subnetwork information be. And at that time, we were using a tool called probing. The probe takes in the representations from one of the layers, and it tries to predict some targets. And we will try to predict the targets that are very syntactical. So we try to predict the syntactic tree length, tree depth, or the tense, or the subject number agreement, these kind of things. And this probing produces a collection of numbers that describe the language model's linguistic capabilities. And those linguistic capabilities are shown to be very relevant for predicting the language model's fine-tuning performance. So after fine-tuning the performance on a downstream task that is partially related to syntax and a lot relevant to many other knowledge, it is possible to make this kind of predictions to a very high performance just using the probing result. So so the this kind of leads to the intuition that from the intermediate representations and other small units within the neural networks, we can find a lot of useful information about a wide variety of the downstream tasks that might or might not appear very relevant to the task that we are testing the intermediate representations on. So here is a recent work that is a work in progress. We try to detect when the reasoning procedure goes wrong, and we are also looking at the intermediate representations. So here is a small visualization. And when the model is doing reasoning, it starts somewhere and ends at somewhere. So on the background, I show a like hand draw visualization of the distributions of the embedding space. So when the model starts to think, it might not directly think about the correct answer, but after a procedure, it can lead to the correct answer, hopefully. But when the model overthinks, in a non-trivial number of times, the embedded semantics drift away. So the model, there are many mechanisms in which the representations drift away. So one of them is that the model apparently works on this problem, but it's actually working on something else. And the model is starts with solving the problem based on the given conditions, but it starts to introduce and consider the information that is not relevant to this problem. And this contributes to the drift away of the embedded semantics. So if we want to stop overthinking, it's better to let the model stop early when we see some early signals when something inside the embedded semantics go wrong. The second intuition is that we know that somewhere inside the model there is the answer, but what is this steering wheel inside the model look like? Should that be a representation of a layer? Should that be a combination of layers? Should that be one MLP? Or should that be several neurons? Or should that be several SAE features? There is the problem of granularity. And usually the way to solve this, tackle this problem is that we first choose a granularity before doing experiments. So we believe that this problem is solvable in that given granularity. And then we proceed with using the approaches to identify the most important parts within that granularity. So but that relies on the assumption, but this assumption could contain could contain many other uh, alternatives. So perhaps it's possible to find the uh, truthful behavior in the geometry. We have seen that in some iClear and ICML papers. It's possible to find the truthfulness behavior in neurons as well, and also the SAE features. So uh, uh, I believe there are still going to be a lot of work that is needed to address this proper granularity problem. So before actually going out to test out the performances of all of those granularities, the field does not know which granularity works the best. And currently, there are a relatively sparse existing works that involve the choice of granularity. So I believe there are still going to be a lot of future works that figures out before we are able to figure out the most appropriate model subnetwork, or in other words, the steering wheel of the model's behavior, especially about the reasoning procedure. So here is a work that we recently try to go beyond one single granularity. So we call this a shift discovery. And in that work, we started to define the subnetwork that connects the model's different modules. But later we thought, why don't we also get rid of 99% of the weights inside the the modules that are along part of the circuit. So when we prune both the edge and the weight, uh, we found that the model's performance still they do not drop by more than 2% on many of the the tasks. So it's possible to figure out the structure that go beyond some presumptions about the granularity. And uh, and also I believe when we consider the uh, a relaxation of the granularity assumption, uh, it is possible to figure out some additional uh, benefits. For example, in terms of the stability or computation cost, or even some performance. You might be even able to find uh, some uh, lottery tickets from the part of the neural network. Uh, but there are still a lot of open problems along the direction. So the first one is that uh, it is hard to find some steering wheels that are highly effective, highly reliable, and highly efficient at the same time. So it's possible to achieve one of them, but usually that comes with the trade-off. We need to sacrifice the properties in the other two dimensions. But ideally, we want to be able to steer the model's reasoning in a cost-efficient way, and we want to uh, make this steering effective and reliable. And ideally, we should have some theories that predict even before doing this steering, how reliable that steering is going to be. Uh, and we should also establish a test for uh, testing for examining the thought process along the reasoning procedure. So even before we need to steer, uh, it would be great that we already start to know that something could go wrong, and it's better to prevent than to try to correct the mistakes when the model already starts to make some crazy decisions. Uh, and there are a lot of new challenges for the safe reasoning, for example, deception, scheming, and resource seeking. So the model's channel of thought might not always be faithful, like the previous speakers say, and the they might appear to some extent hiding their strong capabilities if they are aware that they are being tested on some safety critical uh, uh, tasks. And also when we put the language models in some scenarios where we ask them about some decisions to seek for the resources, there are already some works that realize that the models could demonstrate some resource seeking behavior. So this kind of reasoning behavior could lead to a dangerous path. And up to now, I don't believe the models are capable of making a lot of damage yet. But in the future, uh, as the models become more and more capable, uh, uh, it it is possible that they make more damage than just deleting one source file or several repositories. So yeah, I'm just throwing out these open questions out there for now. I don't have a very good solutions towards those open problems. But I believe the field will figure out a lot of crazy and no, a lot of creative and useful and effective solutions towards many of these open problems in the next few years. So yeah, these are the slides materials that I prepared. Um, I think we have around 10 minutes to take questions. Yeah.
I can start with like one question. So I had a question about the problem of granularity, and I see like a lot of MI papers trying to investigate if there is one like fundamental unit of analysis, like where the things like superposition or polysemanticity doesn't happen, and I wonder like if the problem of granularity is also a function of like task, or do you think like it is like granularity should be like, is it like for some, say for some, if you're investigating reasoning, it has like a different granularity compared to like maybe say like a binary concept like truthfulness or ampleness and stuff like that. What do you think about this? I love to get
Yeah.
your thoughts.
Yeah, very good question. For now, I believe that the appropriate choice of granularity depends on the task and also depends on the data set. And sometimes even if we are analyzing the same task, the way that we construct the benchmark, for example, by writing the question as a multiple choice question versus a binary uh, prediction question versus a generation question, uh, that would affect the the steering wheel that we look for in the answers in the models, because in addition to the functions, there is also the part of the forms, and a part of our answers that we look for from the models are corresponding to the forms of the uh, the questions. And I believe it's going to be very important to consider that and uh, control for the forms. So in this way, we'll be able to focus on the functions, and also perhaps the larger scale benchmarks would be beneficial, because if we're only testing the model's truthfulness on for example, the model's knowledge about the uh, uh, specific domain, then in other domains, the model's truthfulness behavior might be different, and it might be controlled by other parts of the model. So because the steering wheel that we identify from the model takes up such a small part of the model's total parameter, it is possible that there exists some alternate mechanisms. So there was a paper at, I can't remember if it's NeurIPS or ICML last year, that talks about the racing thought. So they say that when solving the problems, there seems to appear a conflict thought process when they use logic lens to look into the intermediate layers. And somewhere inside the model decides to follow one of the mechanism and get rid of the other. So if we only, when we are explaining those mechanisms, if we only explain one of them, we might lead to the illusion of explainability, that we think that we have understand the overall mechanism, but actually there's an alternate mechanism that is not revealed by our current analysis approaches. So in order to be fully faithful to the true mechanisms of the models, we'll need to probably consider that the solutions that we find might not be the only solution that occurs inside the models. Yeah. Thank you.
More questions?
Okay.
Yeah, let's thank Professor Zining Zhu for his amazing talk.
Thank you.